So why don't we talk about some applications?
Yeah, I was waiting because where is this being used? I wanted to know.
You'll be surprised. I mean, this made such a massive contribution to magnetic storage media, right?
That means finally to everybody.
Huh?
Finally to everyone.
Finally to everyone, yeah. And obviously one of the main reasons that those two professors won the Nobel Prize, right? Because it's such a huge success. So, so one of the main applications, actually, I think the first application of GMRs was in hard disk drives.
Okay.
Now here you have a schematic here of how the spin valve type GMR sensors are utilized in hard drives. So if you look at this schematic, you have a recording medium.
Okay.
Okay, now what that recording medium has a certain width and a thickness. Okay, and that's a very thin ferromagnetic. We can think of that as a very thin ferromagnetic medium. Okay. B here is a bit. Now,
okay,
this recording medium has sections where each bit represents one domain. Okay. So far, so good. What else do we have here? Now we are talking about magnetic read and write.
Yeah, so there should be some way to write.
Some way to write. How do we write it?
Means you have to magnetize.
You have to somehow magnetize it, right? So we need to change these directions. That's where this inductive write element comes into the picture. Okay. So we did inductive sensors before. So students should find this very easy. You have a coil here. And then it's wrapped around something like what would you call it? Like a yoke or something?
Yeah.
Yeah, something like a yoke. And that yoke, you can see, has a very localized region here, right?
So the field will be going through the layer, bottom layer.
Yes. So between P1 and P1 dash, right? There's a now this field magnetizes the medium.
Yes.
Right?
Yes.
Correct. In the vicinity of this, let's say this head gap.
Yes.
Okay. Now during this writing, the amplitude of the magnetic field. Now we're talking about the magnetic field of this, right? The amplitude is kept constant. What do you change then?
Direction,
right? So you can easily change direction by changing the direction of the current.
Yes.
And that's exactly what happens here. Okay. So, so depending if you want to write a 0 or a 1, right? So this could, for example, be a 0.
Yeah.
And it could be a 1.
So depending on north, south or south, north.
Yes.
Yeah.
Right? We can
got it.
Do something like this. There's something else, Bobby, we did not talk about.
Green element.
Green element, we'll come to it.
Okay.
What else do we see here?
There is one more.
We didn't talk about. There's one thing we didn't talk about here. If you look at this picture,
I see the coil.
Now we're talking about a very small system here, right?
Correct.
What about these two?
Yeah, I am unable to read it.
Sorry. So there are two magnetic shields on either side to reduce any sort of interference, because again, you don't want this changed. Whatever you're writing is information, and any kind of outside interference could change those domains. So your information could all be wrong. So that's why we have these magnetic shields. Now,
so this will be material with high permeability.
Like shields, yes, correct. Now, on the right, let's say we have this is the magnetization of the.
But where is the GMR or a TMR? I didn't see. You are hiding. Okay.
I'm still talking about the process.
Okay.
No, for me, it's amazing how GMR kind of fit into the picture.
Yes.
So if you take the recorded medium, right, you have to switch the magnetizations.
Yeah.
Right? Let's say this is the BH curve. Again, students know this because we did
the hysteresis loop.
Hysteresis loop, right? We did with the our flux gate.
Yeah.
We talked about the BH curve.
We have briefly discussed this.
Yes, we briefly discussed. But the whole idea is here we are switching magnetizations. Now, if let's say here you have your right head gap, which is what you see here. Okay. Then you want to switch the magnetic domain of one of these sections. Then let's say it's in the positive direction now and it has to go to a negative direction. The applied field must be higher than the coercivity.
Yeah.
Right?
Correct.
And coercivity, again, we talked about that before.
Yes.
So students know that. And then here you have what is called demagnetizing field. When you have certain magnetization, there will be some opposition to it. Right? That's what it's basically shown here. Now we come, where does the GMR fit in here? Here, between this inductive right element and this magnetic shield in green, you have your GMR sensor head, read sensor, to read the information. Now, Bobby.
Yes.
How do you think this GMR now reads? We know we know that the inductive right element writes, zeros and ones onto this medium.
Yeah.
We know the process.
Correct.
How do you think the GMR here?
So GMR is, the field produced by what is that bottom layer?
No, this is not the south.
The bit, what do you call that layer?
The recording medium?
The recording medium is magnetized by the coil.
Yes.
By the writer.
Yes. So it has a certain direction.
Yeah. So GMR can read it. But it can have, whether it is north-south or south-north, it will give same change in resistance. No?
This is what I thought as well. Everyone, I think, when you talk about read heads, because that's very intuitive, right? That's what you think.
Yeah.
And I remember when I used GMR, I thought the same thing. I was like, but in fact, it's very interesting. See, this is a recording medium.
Okay.
So this is, you see, micrometers, So it's tiny.
Correct.
So, which is perfect because our GMR sense is also very small, right? So it's very high resolution. Now, the interesting thing is north-south, right? So any domain will have its own magnetic field, correct? Yeah. In fact, what the GMR reads is the transition points between two bits, right? So let's say you have something in blue and something in red, right? In two different directions. At the transition point between those two, you'll get a positive.
So there will be a point where there is no magnetic field?
Correct. No. If there is no transition, it's a zero.
Yeah.
So, see, if you look at this.
When you say transition, there is one bit. There are, let's say, two bits nearby. So I'm moving above that.
Yes.
Is it like that?
Yeah. Either the read head moves or the recording medium moves. Same thing, right?
Yeah.
So in this case, between, let's say one is in this direction. The other one is in this direction. What the read head reads is this transition point.
Got it.
Right? So in this case, let's say it's a positive. Now,
if they are same, there will not be this. There will not be this change. Okay.
Yes. And if they are the same, as you said, it will be a zero. Which is what you see here.
Yeah.
So 1, 1, 0, 1, 1, 0, 0, 1. Okay. But how does that happen? That's also very interesting. Because if you look at, let's say you have a one bit like this and another bit this way.
Yeah.
Now their stray fields are going to be like this, correct?
At the center, it will be adding.
Now you got it, Boby. Now you got it. So this addition is much higher than the stray field that you can measure here.
Yeah.
Similarly, for other directions, right? If you have it this way now, what's going to happen?
That's also addition, but in the negative direction.
Yes.
In the other direction.
So it's going down here, right? So this is down, this is up, which is why you get a positive here and a negative here. And Of course, if it's in the same direction,
you don't see anything.
yes, because it will cancel. It will go this way.
Hmm.
Now, if it's in the same direction, then you also have this one. Yeah. So in this case, it will cancel. And that's what the GMR spin does. So one is fixed, but the free layer will change according to this increase or decrease. So if you so just to show the students how the layer moves according to this. So if you have magnetization in this direction, that direction, these are your magnetic shields, and this is your spin valve sensor, right? This is your fixed direction. Now let's say your field is at the transition point, the field is up, and let's say this is your free layer initially. This will push it up, right? So that it will eventually become parallel. So you'll see a resistance drop there.
Yeah.
Right, your resistance will drop. Similarly here, if you have the field down, this free layer will go down, then it will be in an anti-parallel orientation.
High resistance.
High resistance, right? So this is how spin valves are used to read the magnetic storage medium data. But
if this was not there, how otherwise I can read?
I think now that's a good question, because I didn't I think
there should be a core, magnetic core, and with a lot of windings,
and pick it up, right?
That is how it's to take a lot of space.
Yes, so it has to be bigger, right?
If I had to get same kind of sensitivity,
yes,
then it will be a big one.
Because students know this. We did search coils, right?
Yeah.
With the core, so they know.
Then I cannot have this compact hard disk.
Exactly.
Also, the speed at which I can read. I mean, the search coil that you discuss, it had some bandwidth.
Yes.
Decided by its parasitic capacitance, coil, inductance, and so on.
Yes.
But here the bandwidth is very high,
which means you can read very quickly. So it's faster, and there you have
small size,
and you can also densely pack more information into a given area. But it has its challenges, right? So one of the things is that you see this is the transition point, right? And these are, let's say, two different domains. Now this is the magnetic field strength. It decreases quite rapidly if you move away.
Yeah.
Right. So ideally you want your layer thickness to be small as possible. But so but this kind of thing that we talked about is called longitudinal recording. But there's a catch here. You see our magnetic sensor here, the GMR.
Yes.
And we talked about how we have two contacts that it provides the current to the GMR. Okay, so the current actually goes through here and comes out here in plane.
Yes.
But when you do that, when you have something like this here, what you're going to do is you're going to limit the distance. Limit the distance you can have between P2 and P1. Because if you put this one here,
it cannot be smaller than that.
Yes. Right? Because the current has to go this way.
So if I want a smaller size to store a bit,
exactly, and you know how important that is, right? Because we want to go smaller and smaller. We want to make the bit size smaller so we can put more information in a given wafer. But with this kind of
the reader limits the
size of the bit. So that's a challenge. So what they did next was they actually changed it to
vertical.
Yes, which is current perpendicular to the plane. So this is current in plane. This is current perpendicular to plane. So this way, now you can make your stack much smaller and then have it here.
Widthwise,
right?
Height-wise, it is saying maybe slightly more because you have one extra layer.
Yes. But width-wise,
not layer, but contact thickness of the contact. Yes, that much it will contact layer, that much it will increase.
Yes.
Okay.
So that was quite good. But then, with this kind of arrangement, you could go up to about 100 gigabits per inch squared. Now, if you have a wafer, right? If you take a square inch and look at how much you can fit in there, you can get 100 gigabits, which is pretty big, right?
Yeah.
But there was a problem. So then what they did was they made it smaller and smaller and smaller and smaller, right? When they made this bit smaller, so let's say initially your bit was this big and you had a certain magnetization. But with this, you could make this smaller, right? So you made it smaller, 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 smaller until you made it
smaller than
very small.
Yeah.
Right?
One domain.
Yes. You're good. Yes. And what happens then?
Then you cannot store.
No. Let's say single domain.
No, but smaller than that is not possible.
Smaller than no. That not that. What happens when it's smaller? It started to the magnetization started to flip due to heat.
Okay.
You make it too small, right? Okay, single domain, fine. You still have a magnetization, but then it's so small. Now it's your
even
heat.
Temperature started affecting it.
Exactly, which means again your hard drive could get corrupted. What do you think they did after that? Solve this problem.
Made it thicker.
They actually changed the magnetization bits to be perpendicular.
Okay.
Right. So again, you have your GMR sensor. Now you've optimized that. Right. Now you made your magnetizations perpendicular, and you still have these transition points.
Yes.
Between these magnetizations.
Yes.
Right. So here you have a transition. It's 1, no transition, 0, and so on. Still much higher than your stray fields. Okay. So you could actually use this kind of arrangement.
Yes.
Which was the, I would say the optimal kind of system that we have now. Here, from 100 gigabits, we could go up to 1 terabit per inch squared. So quite a big difference. So now I think in most hard drives, this is the kind of technology that we have. And GMR sensor. In fact, GMR has also been replaced by TMR. Why? Because TMR, you need current to be perpendicular anyway, because your electrons intertwine. So it's actually the perfect system for this.
Yes.
Right. So, but spin valve type GMRs really changed how we read data. And just for the students' interest, the latest ones, hard drives. These, I think, a lot of the hard drive companies are working on this kind of technology. Again, you have your GMR sensor, but they have two different ways of making things faster and to make the bit smaller. They have what you call microwave assisted magnetic recording and heat assisted.
Heated magnetic recording also.
Yeah, so they have a laser basically to apply heat.
Okay.
So you can quickly change the magnetization. And here the same thing, but they use microwave energy.
Yeah.
To change. But I think these are all in the research stage.
Also, this will be faster than our magnetic writer.
Yes.
And less space also.
Yes. And this could go up to 4 terabit per square inch.
Cool.
Right. So these systems are not out yet, but these are
amazing.
But key point here is without GMR, there's no way this technology would have advanced to this stage, right?
Yeah.
Because to read that, whatever you do with the storage finish, so you somehow need to read it, right?
You cannot read it.
There's no we're only writing.
Yes.
You cannot recover your data.
Yeah.
Okay.